project, we decided to design a self-driving car control system. Self-driving cars are the future. With the increasing populations and increasing drivers on the road, it would definitely increase safety, reduction in traffic, and productive commute times. Safety is a top priority when it comes to driving, especially when they're fully automated vehicles. To ensure safety, we want to design for quick response times, minimal overshoot, and zero error. Here you can see our performance goals. Our rise time is set to be less than 3 seconds. That's basically because we're kind of following up on one of the golden rules of driving and having that 3 second delay between cars. Our settling time, we were aiming for less than 5 seconds because we don't want to do a lot of accelerating and braking, and want to obviously ensure we save the maximum amount of energy in that process. Steady state error is zero. This goes without being said. We'd like to have obviously no error because we want to know where the car is, and avoid any crashes. For percent overshoot, we are trying to keep it as low as we could. We're shooting for less than 5% because we don't want to overshoot and possibly rear end the car in front of us.
All right, as we can see here, this is our plan system for the actual model that we were modeling. Right here, you have a truck that our car is going to be following with our input as R of S, which is the specified distance between the two actual cars. Here we have the system that is modeling our car specifically with the mass of the car and the dampening of that car, which is here used in our transfer function. So as you can see, you have an input R of S, which is set by the user to be a specified distance. Right here, you have T of S, and that is the distance that this truck will be moving along from away from this car. So then by splitting them up using superposition, you get the input, which is R of S, that's the distance that you want your car to be away from the truck, and T of S, which is the actual distance the truck will be moving along. Now, please note, we did split these two for our analysis further during the actual presentation. So we will be analyzing this and this separately with a proportional and furthermore our PD controller. So here are our system parameters. We are analyzing a Porsche 911 GT3 RS, the mass of which is approximately 1,400 kilograms. So then we also looked at the max speed of this car, and in order for us to actually attain the speed, we tweaked the values in MATLAB in order to get our dampening ratio in order to meet that specification or that final speed. So we finally moved on to actually modeling the system with a proportional controller. However, as you can see, our rise time, settling time, and percent overshoot were not met. And that kind of told us, all right, we're going to have to go further and do a PD controller analysis. So with our proportional controller analysis in our open loop, you can see that kind of with the ramp response, it kind of accelerates to infinity because it doesn't have that loop. And here are other things for that proportional controller, which we will not be using and we will discuss further. So here is our proportional controller analysis. This is only our design. So here is our input distance from the car, the actual specified distance that we want to be. And here is our truck distance. So again, these are the two split values using superposition. So here is our final transfer function that we will be using for the system for the distance of the car, R of S. As you can see, our Bode plots and our root locus are looking really good. They are stable, as you can see. And here are our values for that. Our rise time, settling time, and steady state error are on point. However, our percent overshoot is a little bit high, and that's because this is only our design. So we haven't actually put it into the actual proportional design controller loop, which looks a little different. So this is the same thing, except now for the truck. Here we have the transfer function, and here we have the final root locus, and as you can see, is also stable with our final values on the next slide. And our rise time, settling time, and steady state error are, again, as the position of the car, good. However, our percent overshoot is a little bit higher, and that's once again because of the fact that we still haven't put it into the final transfer function or the transfer loop for the proportions.
Now that we know our system is acceptable, that our controller will be able to respond to both changes in input from the user and desired distance, as well as disturbances from the truck, we took our KP and KD values from our design system and implemented them into the actual PD controller. Using these values, we got the same closed loop poles, but without the zero, so that would significantly improve our percent overshoot. You can see for the response to a change in desired distance from the user, RFS, we have achieved a rise time of 1.09 seconds, settling time of 2.66 seconds, steady state error of 0, and a percent overshoot of 2.56% using our PD controller implementation. Here you can see our root locus for this input of the desired distance. We have a little bit of a buffer between where our design goals are and where our system actually stands. So as it wears, it will continue to operate the way we expect it to. However, we were able to meet our constraints. You can see that our step response, especially compared to the design PD controller, it quickly converges to the desired change in distance that we need with minimal overshoot. And for the ramp response, it converges very quickly, so you don't get very much oscillation before it just converges to a ramp and is able to follow the truck as we desire it to. So in response to the disturbance due to the truck moving relative to our car, we analyzed that as well with our controller to make sure it would work. And you can see from our root locus, same story. It's stable, it meets our constraints, and we have a lot of buffer room. For the response due to the truck, we achieved a rise time of 1.1 seconds, settling time of 2.62 seconds, steady state error of 0, and percent error of 1.3%. This is very effective because in general, you have the disturbance of the truck as well as the change in input from the user, but we're able to meet both those constraints. You can see our disturbance quickly converges to 0 with minimal overshoot, and due to a ramp, our car is able to quickly respond and again converge that disturbance to 0. Characteristics of the car. We did this by analyzing the acceleration of the car as well as the power required to make these manual corrections. First, what we did is we analyzed the force required to make a correction between the distance of cars compared to our desired input, and we came up with this transfer function. In order to get an idea what this actually meant in time domain, we took the Laplace inverse and came up with this graph of force with respect to time. Using that, in Newton's second law, we were able to come up with a transfer function for acceleration, and if we assumed a constant input by the driver of the desired distance that we have, we were able to come up with this acceleration equation, 4.95 times our desired correction factor. Now this made sense to us because if you have to make up a larger distance, say 10 meters, you're going to accelerate a lot more, as opposed to if you only have to make up 1 meter, you're not going to use the full acceleration of the car. Additionally, we looked at the power requirements for the car. In our analysis, we came up with a gain of 6,384 or 6.38 kilowatts of power needed in order to make a 1 meter correction between the distance of the cars. Using this information and this torque performance curve for the Porsche 911 GT3, we were able to look at the minimum horsepower, about 135 horsepower to 415 horsepower. That goes between about 100 to 300 kilowatts. And that told us that, yes, this 6 kilowatt correction for 1 meter is a very reasonable value, and it's something that our car would be able to do, including larger corrections. Further analyzing the performance of our car, we looked at the max acceleration of the car from its specified data sheets, 9.92 meters per second squared. And we also looked at its max speed of 68.1 meters per second. Using simple kinematics and the acceleration equations developed in the previous slides, taking into account these max velocities and comparing our accelerations to that car's actual performance, we were able to come up with time estimations for how long it would take to make up certain discrepancies in distance compared to our desired distance between the car in front of us. We determined to make up 10 meters, it would take 1.92 seconds. Make up 25 meters would take 2.74 seconds. And to make up 100 meters would take 5.43 seconds. This does not take into account street laws or anything like that. We just wanted to see if the car was left to its own, how long it would take to correct for these values. These all made sense to us, and they confirmed our results that the PD controller would likely be a good result for controlling our autonomous car. For further analysis, we would like to look into actual experimentation and implementation of the system, modeling it in computer software, as well as actually modeling it on a car or even a miniature scale model in order to see if our results from theory actually match up to reality.